Hi students, I thought I just want to use this opportunity to record a video regarding some of the common calculation you will encounter in acid-base equilibrium. In the past, I often share this with your seniors in a different ways during tutorials. But of course, with technology, I thought I just record it so that in the future, if you need it for revision, you will find it really useful. And then and it actually covers the most quintessential calculation you will ever encounter. And then if you can understand all this, then I guess acid-base equilibrium will never be a very difficult concept for you anymore. Yeah, so I will often start off by sharing with students the titration curve. Yeah, so I need to present a scenario to you so that you will roughly know what is going on. Okay, so I will just introduce you a weak acid. So in this case, we have ethanoic acid. Okay, ethanoic acid over here. And then we will have sodium hydroxide as the strong base. Okay, so we have ethanoic acid and sodium hydroxide as a strong base. Then so there will be two scenarios which you need to be familiar with. So I will illustrate both of these scenarios, but I will just start off by using the simplest scenario so that you will have in mind what exactly I want to present. Okay, so first of all, I will indicate to you the concentration. Okay, so I will use simple numbers so that it's easy for calculation and it's easy for me to illustrate a concept across. So a simple concentration for ethanoic acid will be 0.100 moles per dm cube. Okay, then for sodium hydroxide, I will use the same concentration for easy illustration. Okay, and then next I'm going to showcase to you the volume. Okay, so for the volume, for ethanoic acid, in this case is fixed because I'm going to put it in a conical flask. So this will be 25.0 cubic centimeters. Okay, so I'm going to write in red here because in my first scenario, my ethanoic acid is in the conical flask. So which means it is the one being pipetted out, and then you titrate against sodium hydroxide. Okay, so that means sodium hydroxide is in the burette. And because I give you simple numbers, you can easily tell that the volume of sodium hydroxide I need is 25.0. Okay, I mean, you can work out the calculation quite fast. But I should not put this as 25.0 because it is indeed found in the burette. So I'm just going to write in the burette over here. Okay. Yep. Okay, and then the next information you might need is actually the pKa of ethanoic acid. So the pK of ethanoic acid is 4.76. Okay, so I'll just write it somewhere. Maybe over here. pKa equals to 4.76. Okay. A typical titration curve, right? Okay, of ethanoic acid will actually look like this. So I'm going to have volume, pH as the y-axis. So that's pH. And then I'm going to have the volume of sodium hydroxide over here. Volume of sodium hydroxide. Okay, like this. So this is a titration curve. So I'm going to have a 0 over here. Yeah. So normally, when you draw your titration curve, because this is a mono-basic acid, there will only be one equivalence point. Okay. So I mean, at this stage, you should be familiar with how to draw a titration curve. Okay. Because this is a strong base weak acid titration. Yeah, so you should expect a buffering region somewhere near 4.76. So it's plus minus 1. Yeah, so that kind of details. Yeah, so there should be a gentle outward sloping curve. But other than that, I think you should have a generic idea of how this curve should look like. Okay, so I'm going to just draw it very quickly. So maybe something like this. It's not drawn to scale, so please pardon me for that. Okay, so you're going to expect something like this. Okay, you notice that this part is a bit flat. Okay, so that means that if you draw something like that for exam, you should erase it again because it should come with some slope. Okay, so maybe I will redraw it. Okay, so I'm going to start like this, and then yeah, so this might look a bit better. Okay, with a bit of a slope, right? Okay, so after that, what I'm going to do is I'm going to indicate to you 4 important regions. Okay, 4 important regions for calculation purposes. Okay, 4 important regions. So this is the first region. Okay, I just put it as 1. Okay, and then of course there's another region here which we are interested in. Okay, so this is what we call the half equivalence point. So I just put it as 2, and then after that you'll be over here. Okay, right here. Yeah, so this will be what we call the equivalence point. Okay, so I know this is not really even. Yeah, so this will be 3. Okay, and then after that will be the one in excess. Okay, so over here. Okay, so normally for equivalence point, I'll just put it as V naught. This is the half equivalence point, half V naught, and then this is probably V naught plus V1. Okay, so V naught is the equivalence point. V naught plus V1 means you add maybe in excess of a little bit of sodium hydroxide, so that let's say you want to calculate the pH, you can do that. Okay, so if I can extend the graph a bit. Okay, so it goes a bit out of okay, so if I can extend the graph a bit, yeah, so this 4th point you can actually find out. So this the pH. Okay, so if you are able to calculate all the 4 pHs without referring to your notes and also without much help, that means that you truly understand acid-base equilibrium. Yeah, so in this case, I'm just going to show you very clearly how to attempt the calculation, and then at the back of your mind, I mean, on your free time, you can practice it. Yeah, but I think it's important for you to recognize how to actually perform them during exam. And during exam, we are not going to ask you every aspect of it. We are just going to ask you maybe one aspect of it. Yeah, so you should be very clear. Okay, and remember that the calculation itself is largely stoichiometry. Okay, it has nothing much got to do with acid-base equilibrium. The acid-base equilibrium concept only comes in at the beginning. Okay, yeah. So maybe right now I'm just going to solve for V naught. And remember earlier on, right? I give you simple concentration, and you know that ethanoic acid and sodium hydroxide react in a 1:1 ratio. Yeah. So if I have 25.0 cubic centimeters of ethanoic acid in the pipettes or in the conical flask, then I would expect the equivalence volume, or the volume of sodium hydroxide I need, will be 25.0. Yeah. So in that case, I can easily tell what is V naught. So in this case, V naught will be 25.0, and then the half equivalence point will be 12.5. Okay, because I'm using the burette, so maybe I should add in one more decimal place. Okay, what about V naught plus V1? Okay, so this is a typical question that we often ask. Let's say we exceed by 5 cubic centimeters. What will the final pH be? Okay, so so you can please define your own V1. It's up to you. Okay, so if you want V1 to be 5, let's keep it as 5. I think it's easier. Okay, so let it be 30.00 in that case. Okay, so I exceeded a little bit of sodium hydroxide, 5 cubic centimeters in excess. Okay, so let's try to do the calculation. So the first thing we want to do is to calculate the first pH. Okay, yeah, this is none other than using the very basic concept of acid-base equilibrium, which you studied maybe right at the beginning of the lecture series. Okay, so for revision sake, let's try to do it. So we probably need the ice table. So ethanoic acid equilibrate partially to give me ethanoate. Okay, and H plus. Okay, Yeah, you can put in the aqueous state symbols if you wish, but of course, as a reminder. Okay, so in your ice table, this is the initial concentration. So in terms of moles per dm cube, this is the change in concentration in moles per dm cube. This will be the equilibrium concentration in terms of moles per dm cube. Yeah, and because we start off with 0.100, okay, so we try to fill in the table. So we have 0.100, so we have dash here, and then minus x plus x plus x, because they dissociate in a 1:1 ratio. So if this decreases by x, the other two will increase by x amount. Okay, and then of course this will be 0.100 minus x, and then x. Okay, then using simple acid-base equilibrium concept, here we are actually defining Ka. Okay, Ka is the acid dissociation equilibrium. So in that case, Ka will be equals to the concentration of ethanoics. Okay, equilibrium concentration of ethanoic multiplied by the equilibrium concentration of H plus divided by the equilibrium concentration of ethanoic acids. Okay, right, and then from here you can equate to x squared over 0.100 minus x. Okay, then right now you can take your calculator, because you don't know Ka, but you know pKa. Yeah, so you know the relationship between pKa and Ka, I hope. Right, so in that case, I'm going to have 10 to the power of minus 4.76. Okay, is approximately equals to x squared over 0.100. That's because this is assuming that x is much smaller than 0.100 moles per dm cube. Yeah, you need to take note of this particular assumption when you are performing the calculation. Okay, so in that case, we'll try to solve for x. So 10 to the power of 4.76. And then we multiply by 0.1. Then we take the square root. Okay, so we get a certain numbers for x. That's the concentration of H plus. Yeah, so I'm going to write it here. So x is thus equals to 1.318 times 10 to the power of minus 3 moles per dm cube. Yeah, and x essentially is the concentration of H plus. So we take negative log base 10. So negative log base 10. And then we get 2.88 as the pH. So therefore, pH is equals to 2.88. Okay, so we have successfully calculated this. So this is 2.88. Okay, by simply just applying a simple acid-base equilibrium concepts. Okay, then next we need to calculate second point, but we don't really need to calculate. If you recall, again from acid-base equilibrium, this is essentially the half-equivalence point. Okay, what do I mean by the half-equivalence point? Yeah, so that means that half the amount of ethanoic acid has reacted away. Okay, so for those of you who forgot, I can do a simple proof here if you want. Okay, so you know that Ka is actually equals to the concentration of ethanoics, equilibrium concentration, H plus, and then concentration of ethanoic acid. Okay, if half the amount of ethanoic acid reacted away, yeah, so at half, you can call it half neutralization point or half equivalence point. Okay, so that will mean that the concentration of ethanoic acid equals the concentration of ethanoics. Okay, so when that happens, these two will cancel out. So when these two cancel out, therefore pH equals to pKa. Yeah, so for the experienced students, you don't need to calculate 2 because 2 essentially is 4.76. Yeah, and those of you who are experienced, you probably know that this is actually the buffering region. Yeah, okay, so this region is actually the buffering region. I think in the notes is defined as pKa plus minus 1. Okay, so therefore the ratio of ethanoic to ethanoic acid can range between 1 to 10 all the way to 10 to 1. But this is not a lesson on buffer, so I'm not going to go into buffer as of now. But you realize that for this region, as you add as you add sodium hydroxide, as you produce more and more ethanoate, you are sort of creating a buffer. So that's why there is sort of a resist in the change in the pH. Yeah, so but it increases in quite a gradual manner. Okay, of course, until it hits the equivalence point. Yeah, and then after it will shoot up. Okay, yeah. Then of course the next thing is what is the pH of the equivalence point? Those of you who can remember some basic idea, you will remember that for a strong base weak acid titration, the equivalence pH is greater than 7. Okay, so the equivalence pH is greater than 7. Then in that case, if it's greater than 7, can I just put greater than 7? No, you can't do that because you have to calculate. We need you to calculate to ensure that you know what exactly is going on. Okay, so if we need to calculate, then what do we need to do? Yeah, so that's the most difficult part of essay-based calculation for most of the students. I mean, in general, I think most of the students found doing this to be very difficult. Okay, so I put a double star here. Okay, but if you are very sharp, you will know that it's not that difficult. So I'm going to just illustrate to you over here. How can we actually perform the calculation? Okay, so but before that, maybe I'll just erase this part away because earlier on I'm just trying to prove to you how to calculate the half equivalence points. Okay, I think first of all, right, we need to understand that at the equivalence point, at that instance, what you have is solely ethanoate, which is the conjugate base of a weak acid. So the conjugate base of a weak acid itself is also a weak base. So a weak base, what's going to happen? It will undergo partial ionization in water. Yeah, so sometimes another term we use often in lectures is partial hydrolysis. So if it undergoes partial hydrolysis in water, how does it look like? Okay, so we have ethanoate over here, plus H2O, equilibrate to give us ethanoic acid plus OH minus. Okay, so this represents the partial hydrolysis of ethanoate. Okay, so I repeat, the ethanoate is the conjugate base of a weak acid. So itself is also a weak base. Yeah, and then we're going to do the same thing over here, except that we are not defining Ka here. We are defining Kb. Okay, so remember this. When we are dealing with weak acids, we are looking at acid dissociation constant. When we are dealing with weak base, we are looking at base dissociation constant. Okay, so we are dealing with Kb here, but we don't know Kb, right? Am I right to say that? We don't know Kb, but we know a relationship between pKa and pKb and pKw. I mean, at 25 degrees Celsius room condition. Okay, I mean, yeah. So in that case, we know that pKa plus pKb is equals to 14. Right, we know that. Okay, so in that case, we can easily find out what pKb is, which is simply 14 minus 4.76. So that will give us 9.24. Right, 9.24. So in this case, we know this indirectly. Okay, so with that, we can create an ice table. So again, the same thing. Ice, in terms of initial concentration, the change in concentration, and the equilibrium concentration. Now, truth to be told, right, this will often pose a challenge to students. The one I boxed in red. Yeah, the concentration of ethanoate. Because in most cases, the student will say 0.100, but it's not 0.100. Why is that the case? Because the total volume changed. We started off with 25, okay, with 0.1 moles per dm cube. So in 25 cubic centimeters, you can easily scale the amount of ethanoate to 25 cubic centimeters, right? Okay, but now at the equivalence point, the volume doubles from 25 to 50, right? Because we need to include the volume of sodium hydroxide which we have added into the solution. Yeah. So in this case, it's just nice because I'm using simple numbers. So the volume doubles from 25 to 50. So if the volume doubles, concentration will half. I hope you get that. Okay, so in this case, the concentration will be 0.0500. Okay, and then I avoid using X. I should be using Y in this case because X has been used. Okay, and then of course 0.0500 minus Y, and then Y and Y. Okay, and then of course we are defining KB. So KB is equals to Y squared over 0.0500 minus Y. Okay, we can easily determine KB from PKB. So that will be 10 to the power of minus 9.24 equals to Y squared over 0.0500. And of course, the assumption we make here is that Y is much smaller than 0.0500. Okay, so with the same thing, I'm going to use a calculator to determine Y. Y actually gives us POH, and then we can find out pH. Okay, so we'll use the calculator. So 10 to the power of 9.24 minus. Okay, and then I'm going to multiply it by 0.05. Okay, and then I'll take the square root, and that will give me 5.363 times 10 to the power of minus, let me count the zeros, 1, 2, 3, 4, 5, 6, minus 6 moles per dm cube. And then I'm going to find the POH, so minus log base 10 of that. So that will be 5.27. And then I'm going to find out the pH, which is 8.73. Okay, which is reasonable, right? Because it's slightly above 7, but it's not like way higher. So yeah, so this is reasonable, 8.73. Yeah, so therefore, the third pH we're going to calculate will be 8.73. Yeah. I hope the students recognize that I'm using a simple scenario. If the concentration is different, of course the equivalence point will not be exactly 25. It will change a little bit, and then you have to scale accordingly. So it will not be such a nice, simple way of calculating the concentration of ethanoic. So I hope you recognize that, and then do the necessary scaling. As I mentioned, the concept of acid-base equilibrium is usually applied right at the start. Yeah, but in the course of doing, we are really looking at whether you are able to perform simple mole concept calculation. If you are able to do that, I think it shouldn't be a major problem. And you will see that for the fourth pH. You will see that for the fourth pH. Okay, so okay, I'm going to illustrate to you again how to calculate the fourth pH. It's actually very easy because you know that the excess 5 cubic centimeters will essentially force the pH to go very high up. So you will just go all the way maybe to 12-ish, 13. Yeah, if you don't believe, we can do a check. Okay. Now, I'm going to erase this portion so that it's clearer. Okay, so first of all, right, let us just try to imagine a little bit. Why is the pH at the equivalence point above 7? Yeah, okay. It is actually due to the slight excess of OH minus in the system. Okay, due to a little bit of OH minus in excess, which is a resultant from the partial hydrolysis of ethanoic, or you can say partial ionization of ethanoic. Yeah. In that case, right, when I add OH minus between 25 to 30, so there's an excess of 5 cubic centimeters. What do you think is the amount of OH minus added? I mean the absolute amount. Okay, we can try to calculate that because we know the concentration of sodium hydroxide. So if we know the concentration of sodium hydroxide, then we can actually calculate the number of moles of sodium hydroxide in 5 cubic centimeters. Okay, so we can easily do the scaling. So that's 0.1 divided by 1000 times 5. Okay, so that will be 5.00 times 10 to the power of minus 4. This is in moles. Okay, so this is the amount of OH minus in 5 cubic centimeters of the added sodium hydroxide. Yeah. If you try to scale it to the concentration, okay, so that means that from this value, you divide by the total volume, which is 30 plus 25. So the total volume is 55 cubic centimeters. So I'm just going to scale the total volume. You notice that the concentration of OH minus, right, in this case, is actually 9.091 times 10 to the power minus 3. This is solely due to the extra OH minus added. Okay, so if you are confused, let's try again. Okay, let's try again. The amount of excess OH minus, which is between here to here, in 5 cubic centimeters, is actually 5.00 times 10 to the power minus 4. How do we do that? Basically, you take the original concentration of sodium hydroxide, you scale it, so you divide by 1000, you find out how much is in 1 cubic centimeters, how much is in 5 cubic centimeters. So this is the amount. Yeah, if you want to find the concentration, we need to divide by the total volume, which essentially is 25 plus 30. Okay, why not 25 plus 25? Because we added excess of OH minus, so we need to account for the extra volume. So that would be 5.00 times 10 to the power minus 4 divided by 55 times 1000. So it's similar to divide by 0.055 because I'm using dm cube as my denominator unit. So I get this concentration. Now, did you notice that this concentration, in terms of the power, okay, so in terms of this particular power, we are looking at minus 3 here. Here we are looking at minus 6. So it's like 1,000 times greater. So to make our calculation simpler, we can actually just ignore this, okay, because the addition of OH minus will actually suppress the ionization of ethanoic. Yeah, it will suppress it. Okay, so this will be a very good proxy to the total amount, or rather to the concentration of OH minus in the medium after 30 cubic centimeters of sodium hydroxide has been added to 25.0 cubic centimeters, 0.1 moles per dm cube of ethanoic acid. Okay, so if this is a good proxy, then we can straight away calculate the pOH. Am I right to say that? Okay, so we can do that. Then okay, we'll try to calculate the pOH. So that will be minus log base 10. Okay, that will be 2.04, right? 2.04. Okay, so we get 2.04. Then so therefore pH essentially is 11.96. Okay, so can you see that it's very close to 12, right? 11.96 essentially is this. Okay, yeah, so I hope you find the explanation to the calculation of the individual pH useful. And it is important for you to be able to work through the calculation on your own easily. You can actually set your own questions, meaning that you can do your own calculation on your own at home. You can randomly choose a HA. Okay, so that means that okay, I'm just going to erase this portion. Okay, because I think they are a little bit messy. Okay, so and then after that, I'm going to explain to you what I really mean when you choose a random acid. Okay. Okay, so you can actually just choose a random acid HA and then a base sodium hydroxide, and then give your own concentration, any values you want, but not ridiculous values. I mean the concentration can be between 0.1 to let's say 0.3. Okay, so any concentration you want, 0.0500 all the way to 0.300. You do the same for sodium hydroxide. Okay, and then the volume you pipetted in, okay, you can decide. Okay, the standard pipette volume is 15.0 to 30.0, for example. And then you can do this in the burette. Okay, then you can choose your own pKa of the weak acids. Okay, so pKa maybe any values between say 3.5 to 5.5, something like that. Yeah, just random, you know, like, and then perform your own calculation. And then after that, you swap the two. So before you perform the calculation, sketch the titration curve. Okay, sketch the same titration curve that I've just sketched. Swap the two. And perform the calculation. I mean, sketch the titration curve again and then perform the calculation. So I have not done that earlier on. I have not swapped the two. I'm going to do that very quickly later. Okay, so what do I mean by swapping the two? So in that case, in this case, the volume now, I'm going to put HA in the burette. And then, of course, the sodium hydroxide will be a pipetted volume. So this will be between, again, 15.0 cubic centimeters to 30.0 cubic centimeters. And then after you perform the same calculation again. Okay, yeah, so to lead by example, I'm just going to do the reverse calculation for you. Not exactly reverse, but instead of putting sodium hydroxide in the burette, I'm going to pipette it out to put it in the conical flask. And then I'm going to put ethanoic acid in the burette. Okay, so just going to show you how the calculation will look like. Okay, so I'm going to erase this part because the titration curve will be different. And if you want, you can pause the video for now so that you can look at the answers later. Okay, just check your answers. Okay, so I'm going to do the same thing. I'm going to write down the volume. So the volume, I'm going to put ethanoic acid in the burette. And then sodium hydroxide in the conical flask. That will be 25.0. Okay, and then of course the pH curve will look like this. Titration curve, so 0, and then in this case, instead of volume of sodium hydroxide, that will be the volume of ethanoic acid. Now, the graph is not only, instead of going like that, now it's the other way around. It's not only like that, okay, but the buffering region is different. So just ask yourself this question. Where do you think the buffering region is? Okay, so pause the video, think about it, and then continue after you have thought through it. Okay, now remember that what we have in the conical flask is actually sodium hydroxide, which is a strong base. Okay, so even when we add ethanoic acid to it, I expect it to be relatively flat so that it won't be affected too much. Okay, so I mean, it will not be a flat line, so it will curve down a little bit, but it will be almost flat. And after that, it will just curve down like this. Okay, so you look largely this kind of shape, although I don't think my drawing is fantastic, but I don't think it matters a lot here. Okay, now the first thing is, of course, you need to know the initial pH. Okay, which you can do that quite easily. You need to know the pH at the equivalence point. Okay, so that's number 2. Now, common misconception, the students think that this is the half equivalence point. Remember this, the sodium hydroxide is in the conical flask. So when you add your ethanoic acid in, immediately your ethanoic acid will become ethanoate. So there is no accumulation of ethanoic acid. If there is no accumulation of ethanoic acid, there will not be a buffer, okay? So all the ethanoic acid will have been reacted. The buffer will only begin after the equivalence point. So over here, then, it is meaningful to talk about the pH of the maximum or at the maximum buffer capacity, or what do you think the volume is, if you know where I'm coming from. Okay, so if I reverse the thing, actually the calculation to some extent is actually more straightforward. I mean, to some extent. Okay, so first of all, what is the initial pH? Okay, in that case, because it's 0.1 moles per dm cube, okay, even though I have 25.0 cubic centimeters, the concentration is still the same. So minus log base 10 OH minus concentration, POH will be 1, right? If you punch a calculator, minus log base 10 1 is, minus log base 10.1 is 1, and then after that pH is 13. So the first pH over here. We're going to calculate with 13, right? How about the how about the equivalence point? Well, the equivalence point, I think you can agree that it will be similar, or you'll be the same as what we determined earlier on. Okay, so what do we mean by what we determined earlier on? Okay, when all the OH minus has been neutralized, so what do you think is the volume of ethanoic acid I need? You'll be the same, right? Because they share the same concentration. So the total volume of ethanoic acid I need for complete neutralization, it will be 25.0, right? Yeah. And because it's 25.0, what is the amount of ethanoic acid in 50 cubic centimeters? Yeah. So can you easily perform that calculation? What's the total volume? Oh, sorry, what's the total amount in 50 cubic centimeters? I think you can easily perform that calculation, and then you will be able to determine that the amount of ethanoic will be half of 0.1, so that will be 0.050. So you go through the same calculation because we are looking at ethanoic acid. The pKa is 4.76, the pKb will be 14 minus 4.76, that will be 9.24, right? So if you do the same calculation, I think you'll end up with the same number. I forgot what's the number we had earlier on. But never mind, for the authenticity, we can perform the calculation again. Okay, so we're just going to do the same calculation. So as to prove to you, showcase to you how it can be done. So pKb in this case 9.24. So we have pi stable, and this is 0.0500. So dash dash dash, minus y plus y plus y, and then 0.0500 minus y. So this is y. Okay, so Kb, which is equals to 10 to the power minus 9.24 equals to y squared over 0.0500 minus y. Okay, so we solve for y, and then we find pH. Okay, so I'll just do a quick one over here. Okay, so same thing, 10 to the power 9.24, and then multiply by 0.05. Of course, we assume that y is much lesser than 0.05 moles per dm cube, and then with that number we take the square root, and then we take minus log base 10 of that. Okay, and then we will add 14 to that, so that will 8.73. Okay, yes, that's the number. So we get 8.73. 8.73. Okay, so this so number 2 here will be 8.73. Okay, then the next question you might want to ask yourself is what is the volume of ethanoic acid I need to add in order to get the point where it demonstrates maximum buffer capacity? Common misconception students have is half of this, which is 12.5, but it's not. The reason is the amount of ethanoic you have over here, right? You can easily calculate because you added 25, right? So it's essentially 0.025 multiplied by 0.1. So you have 0.0025 moles of ethanoic. Yeah. So in order for me, because maximum buffer capacity occurs where the amount of the conjugate base is the same as the amount of ethanoic acid. So in order for you to have 0.0025 moles of, you have 0.0025 moles of ethanoic. So in that case, the amount of ethanoic acid I need will be 0.0025. So in order for me to achieve 0.0025 moles of ethanoic acid in excess, I will not add to 12.5. I will need to add another 25. Yeah, so for titration involving strong base and weak acid, when you are placing the strong base in the conical flask, that means you do the titration the other way around from the start. Yeah, and of course the graph is also the other way around. The volume of ethanoic acid you need to achieve maximum buffer capacity is actually double. Okay, so that will be 50.0. Yeah, so this is the point where maximum buffer capacity occurs. So this is max buffer capacity. And then what you're going to get here is this will be 4.76. Okay? Yeah. But for the record, right, may I suggest that you do not memorize all this. Yeah, don't memorize that, like for a strong base weak acid titration, if the weak base is in the if the weak acid is in the conical flask, maximum buffer capacity is half equivalence point. When the strong base is in the conical flask, then it's double equivalence point. I think there is really no point in remembering all this, because the idea is, as long as you think about it from the conceptual perspective, from working out the problems using simple stoichiometric calculation, simple stoichiometric ideas, etc., then you realize that all this you can actually derive quite easily. Yeah, so that's really my suggestions. And I think that's about it. And do expect more videos on acid-base equilibrium to come along. But at least for now, I think I have showcased to you the quintessential points of acid-base equilibrium calculation for your revision. Remember that this is for your revision, which is very important. And on your own accord, I really recommend you to design your own questions and then work throughout whenever you are free or on your way home. Yeah, if you are able to design one question a day, you do it once. I think you'll find that working through the problems is very easy, and you do not have much issue in tackling even exam questions. Remember that learning this is not about exam questions. Learning this is really about also thinking through what exactly is happening in the course of the reaction. And if you truly understand a lot of these concepts, you realize that you do not need to revise a big chunk of acid-base equilibrium for your assessment. And then that actually allows you to actually save the time to do other things. Okay, yeah, so thank you for watching the video. So do expect more of such videos to come along.